We are good to go.
Requesting all the participants
Powering on.
to mute your microphones, please. Requesting the participants to please mute your microphone. A very good evening, ladies and gentlemen, and a warm welcome to this event. I am Maria Beatriz D'Souza, Faculty Associate Professor at St. Xavier's College, MAPSA. And I have been assigned with a very pleasant task of introducing our speaker for this evening, Reverend Dr. Richard D'Souza. Many of us think and believe that religion and science are at odds. But our speaker for today is both a scientist and a Jesuit priest. Reverend Dr. Richard D'Souza made international headlines for his study on the long-lost sibling of our galaxy, the Milky Way. A son of the soil, Dr. Richard did his schooling at St. Brito's MAPSA, and I'm indeed delighted to also state that he has studied as a +2 science student at a higher secondary, that is St. Xavier's MAPSA, Goa. He completed his college education degree from St. Xavier's, Mumbai, and did his master's and doctorate in Germany. In 2018, he enrolled for postdoctoral research studies in the University of Michigan and is part of the prestigious Vatican Observatory at Rome. This evening, we are looking forward to gaining significant knowledge and insight in the world of astronomy from Dr. Richard D'Souza. He has been a recipient of many prestigious awards and scholarships. On behalf of the Friends of Jesuits of the Goa province, I welcome our very own astronomer priest, Reverend Dr. Richard D'Souza, the pride of Goa and of the nation. Our distinguished speaker, being a fellow Goan, it wouldn't be out of place for me to welcome him in our mother tongue Konkani. Dr. Richard D'Souza, तुमका येवकार आणि तुम्ही हांगा आयले, आमका वेळ दिलो म्हणून तुमका देव बरें करूंक म्हणटा. आणि सगळ्यांक हांगा हाजीर आशिल्ल्यांक तुमका एक बरी सांज हांव दिता. Thank you. Before Dr. Richard D'Souza takes over, I'm requesting all the participants to please mute your microphones and turn off their cameras. Also, participants, please note that you could ask questions at the very end of this session. Please note that the series will continue tomorrow at the same time, and you can use the same link. Requesting you once again to please mute your microphones and turn off the cameras. Thank you. Father Richard, over to you now.
Father, unmute yourself. You need to go to the Google Meet screen and there you'll find the option. Just click on that mic option.
Okay, can you hear me, everybody? Hello?
Yeah, Father.
Can you
It's
hear?
clear,
Okay, good.
loud and clear.
Sorry, everybody, for the delay. I am also learning to use this new platform of Google Meet. So welcome. Let me start immediately. If you can see my screen, you will see a screen which says 5 ideas that change our understanding of the universe in the last century, a brief introduction. Let me go ahead. So let me start off by saying very intuitively that as human beings, as we have looked up in the night sky,
Father, you are muted. You're muted.
Father, you're on mute again.
okay, is it better now? Can you hear me?
Yeah.
Okay. So please warn me if I am muted again. Okay. Yes. Okay.
Sure, Father.
So we are talking about the fundamental questions in astronomy. So first, the questions are of what is our place in the universe, and we ask these questions from centuries about in 4 possible forms. How big is our universe? Where do we come from? Where are we going? And are we alone in the universe? Okay.
Yes.
So these are the 4 basic questions which we are trying to answer in astronomy. Now, I will today try and answer these 4 questions from the perspective of what we have learned in this last century, which means from 1900 up to now 2021. And I have listed 5 points which we have learned something really dramatically new in this century. The first is the size of the universe. The second is the origin. How did the universe start? In the third, our own origin. How do the elements that make up our body, where do they come from? The fourth question, the fourth idea, is about the end of the universe. What will happen at the very end? And the fifth question, the fifth topic is related to the question, are we alone in the universe? And this is the recent discovery of what we call as extraterrestrial planets and the search for signatures of life in outer space. Now, I also have to add one more topic to this, and that is, to understand this, we must first know what was the past understanding in the 19th century. So in reality, I have 6 topics. I have 6 topics, and I will talk about the first 3 topics. The first, the past understanding, size, universe, and the origin of the universe today. And the last 3 topics, I will talk about them tomorrow. So without further ado, let me just briefly state what I want to achieve in these 2 hours which we have. I'm going to talk about these topics in 2 hours, and I'm going to give you a brief overview, a very general view. So think of yourselves cruising in an aeroplane at 10,000 meters, and we are going to see things from really far away. We won't be getting into any details. But the important thing which I want you to get is to understand the basic concept and to develop an intuition about it, so that you can actually go and even tell your friends about it. In choosing these 5 topics also, I am recounting the story of astronomy from my point of view. There may be other ways of doing it, but these are the 5 things which came to my mind. And I will also warn that during this 2 hours, I will not comment about the intersection of science and faith. For a simple reason is that I believe that first, to talk about the intersection of science and faith, we must know what science tells us about what science is. We must know what faith tells us about faith. And only then we can talk about the intersection. And we will leave that for another session in the future. So without further ado, let me now go to the first topic we will deal today. What was our understanding of the universe in the 19th century? So before 1900. So for a long time, we knew that there was the sun, which is, I have depicted over here, and there are the various planets. So you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So we could safely say that even, and Pluto, before 1900, we knew about the existence of the planets. We could see them in the night sky. We knew some of them had moons, and I'm showing you the moons over here of Jupiter and the moons of Saturn, even the moons of Uranus. We knew all this. And we knew that these, we even had some rudimentary idea of how far these things were away from us. So if I would briefly explain to you that if we consider the distance from the Earth to the Sun as one unit, which we call as one astronomical unit, then we could say that the distance from the Sun to the furthest object, let's say Pluto or maybe Neptune, is about 30 astronomical units. Okay, one astronomical unit is almost 0.1 billion kilometers. So it's a very large unit. But because distances in astronomy are so large, we will be inventing new units. So let's get familiar with this unit. One astronomical unit is the distance from Earth to the Sun. And then we measure everything in terms of those units. But this is really big. That means from the Sun to about Pluto is about 30 astronomical, 30 times the distance from the Earth to the Sun. Let me also briefly state that if you also have questions, I would suggest that you actually type them down in the chat. And towards the end, I can help you 5 minutes of the talk. And tomorrow, in the beginning of the talk, I will answer some of those questions. So we knew about the planets in the solar system. We could see them moving. Okay. We also knew about comets since very old. We knew, people always thought that comets were bad omens. So where do comets come from? Now, if you would, again, I'm showing you another picture of the solar system. Right in the middle is the Sun. You can see in green over here is the orbit of Saturn. Then you have Uranus in pink. The orange is Neptune. And the orbit of Pluto is slightly inclined from the orbit of Neptune. So if this is what we saw in the previous picture, if we go beyond it, there is something which is called as the Kuiper belt. And what is this Kuiper belt? It's a place where there are a large number of rocks. You can think of them as asteroids, icy objects. And ever so now and then, one of them gets displaced and comes rushing towards the Sun. And people kind of knew this before the 1900s. And we realized that these objects which were coming from very far away, were icy objects, and were coming far away and heading towards the Sun. And in this picture, you also see, now not the 1900, but a present most distant man-made satellites or messengers, Voyager 1, Voyager 2, Pioneer 11, New Horizon, and Pioneer 10. They've actually now crossed the confines of our solar system and have also reached beyond the Kuiper belt. We also knew this to we also think, let's put it this way, we also hypothesize that beyond the Kuiper belt there is something much further out, which is called as the Oort cloud, another region of icy objects from which a number of comets also originate from this. But now if you look at this plot, you will see that the distance from the Sun to the Earth is 1. The distance from the Sun to Neptune is about 30. The distance of the Sun to the edge of our solar system is 100. So that's where Voyager 1 is now. And then beyond that is the Oort cloud. And we kind of understand, yes, there are things much beyond that. But before the 1900, we also knew about stars. And one thing which the early scientists realized is that the stars don't seem to move in the night sky. The planets move instead. Comets move. So why is that some objects move and some objects do not move in the night sky? And the basic understanding which people had in the past is simple. Anything which is close by to us, we can see it moving. If anything is very far away, we will not see it moving. So people understood that the stars are very far away because we cannot see them moving in the night sky. The planets and the comets we can see moving in the night sky. So right in about 1838 was the first time we were able to actually determine the distance to the nearest star available, or to the closest stars available. And the way they did it then was a technique which is called as parallax. Now, what is parallax? All of us are familiar with parallax. When we look at a distant object, just put this, you take your finger, put it in the object, and if you move your head, you can see that your finger is actually moving behind a reference frame, behind the wall or behind your computer. By moving your head and you're keeping your finger fixed, you are actually being able to see that it moving. But if your finger was very, very, very far away, you realize that it won't move that much across the night sky. So let's look at this figure over here. Let's say we are now the Earth, which is moving around the sun, and we want to determine the distance to a group of stars, which is called as the Pleiades. This is an example. So what people did was they observed these stars in February. Let's say for an example. And then they waited for the Earth to go around the sun and wait till exactly the opposite. And they observed the same set of stars. And what they realized was certain stars seem to slightly move behind some other far away distant objects. And in this way, they could actually measure that the stars have slightly moved, and they could measure an angle, which is called as the parallax angle. And using this parallax angle, they could actually determine the distance to the star. But let me just take a step back and explain something first to you first. First, let's keep in mind that stars have a certain brightness. And if it's a star is very close to us, it will appear much brighter. If it's very far, it will appear less bright. This is our common experience. Even if you look in Goa and look at lights as you're cruising in a car, you will see lights closer to you, lights very further away from you, and the brightness depends upon the distance. But it also could be that the various lights have various different brightnesses. So just going on the brightnesses doesn't really make a difference. You really need to have what is called a basic trigonometric, a geometric way of determining the distance. And this way, by actually using the way that the Earth goes around the sun, and it's a big distance that the Earth goes around the sun, and you're actually looking at nearby stars and trying to find out how they are moving in the night sky. By a slight shift, you could actually try and determine that distance. So the first time the parallax of a star was measured is only in 1838. And it's actually a proof that the Earth is going around the sun. Now, just to put this in perspective, if the distance to the Earth to the sun is 1 AU, and if you move around, right, so you have a baseline of about 2 AU, 2 astronomical units, and 1 arc second, which is now, let's try to say what is an arc second. For most of you will know this. So think of a degree. All of you know what a degree is. So 360 degrees makes a full circle. You have 1 degree. 1 upon 60 makes a minute. 1 upon 60 makes a second, arc second. So it's like 1 upon 3,600 of a degree. And if you make that angle you would achieve a distance of what is called as about 1 parsec, which is a very large number. It is like, as you can read over here, 206,000 AU. So let's put it this way. I put here some basic units we use in astronomy. You quickly realize that kilometers is useless for us because distances are really large. In our solar system, we will use astronomical units. For much larger distances, we will use light years. But even much more larger distances, using the system of measure, which is using this angle parallel, we will be talking about 1 parsec. 1 parsec. PC is 1 parsec, which is 206,000 AU, astronomical units. So in this way, you can actually measure by basic trigonometry, which all of us learned in school or higher secondary. You can actually measure, by measuring this angle, you can measure this distance. So before 1900, we actually measured the distance to about 60 closest stars. I tried to illustrate this over here. So this is the sun over here. And we have measured the distances to various stars. Some of you may recognize some of these names. Vega, Alpha Centauri. Alpha Centauri is the closest star to us. It is a distance of 4.37 light years. It takes light 4 years, approximately 4 years, to leave Alpha Centauri and to reach us. And in our new units, this is about 1.34 parsec. Then you have Vega, which is also very famous. This is about 7 parsecs away. And then you have Arcturus, which is another famous star. It's available at 11 parsecs. So let's put it this way. At the end of the 19th century, we had this understanding that there were these stars. There was a solar system. There were stars much further away. Some stars we could make out the distances, and everything else was much further away from here. What else did we know at the end of the 19th century? There was a person by the name of Messier. He was a French person, French scientist. And in 1774, he looked at the night sky through his telescope and he looked at all these strange objects. And he called them nebulae. Now, this Messier was only interested in the 18th century in comets. Now, comets, as we remind ourselves, comets and planets move in the night sky. And if you've ever seen a comet, you see it's nebulous. It's kind of fuzzy. It's not like a star. It's kind of an object with a long tail. But when he looked at these objects, of course, these are much more recent images, so they look much more nicer. But he identified about 100 such objects which were nebulous, cloudy, but which were very strange. They didn't actually move in the night sky. They were fixed. So he was like, I'm interested in studying comets. So I'm just going to name these things, find their names, catalog them, and forever remember that these are not comets because I'm only interested in comets. And we actually have these names of these various Messier objects. They are like nebulous objects in the sky. Okay. So this is what people knew. People did not know the distance to these Messier objects even then. Let's now move one step ahead, cross the 19th century, the thing of the 19th century, enter the 20th century, and ask, what did we learn in this 20th century? The first thing we learned in the 20th century is that the universe gets bigger. So from what we knew, it gets much, much bigger. Let's try and understand this. Now, I'm going to put some information which may not make very much sense to you, but we will learn this a bit more later. So what I'm showing here is a diagram about the various types of stars in the night sky. And what you immediately note is that let's look at this figure. And on this figure, I'm showing you two things. Concentrate on this side, on this axis, the y-axis, the vertical axis. It is in units of luminosity compared to the sun. So if you look at the sun over here, you will see that there are stars which are 10 times much more brighter, 100 times, 1,000 times, 10,000 times, 100,000 times, much better than the stars. And there are stars which are even more dimmer than the stars, than the sun. So stars have various intrinsic brightnesses. So this is one thing to remember. They have various intrinsic brightnesses. They also have something which are colors. Some stars look red. Some stars look blue. We'll come to understand this. They're actually related to the temperature of the star. Some stars are red. Red is actually cooler. Just remember this. Blue is actually much more hotter. And we can actually measure both the luminosity and the temperature of the star. So this is more recent knowledge, but this becomes important to understand what comes later. So these are the intrinsic brightnesses. But now if you scatter these stars in space, some closer, some further away, all these brightnesses shift, because if it comes closer, it becomes more brighter. It appears more brighter to us. If it goes further away, it appears much more dimmer to us. So one thing, in the start of the 20th century, there was a lady called Henrietta Swan Leavitt who were observing a particular type of stars which were living in this region of space over here, which is just my mouse pointer. And these stars are called as the Cepheid variables. Now, the particular things the astronomers noticed about these stars is that the brightness of these stars changed over time. Sometimes they became brighter, they became dimmer, brighter and dimmer. So you can see the luminosity changes over time. It's a single star, but somehow something happens within the star and the luminosity changes. And this lady, she was working in Harvard through various observations. She realized that actually this period of this kind of change in luminosity is related to the brightness of the star. So if brighter stars take longer time, so the longer change in time, whereas less bright of these Cepheid variables, this particular type of star, if it's less bright, it quickly changes in amplitude. So it means becomes, let's say within 2 or 3 days, the amplitude changes. But if 3 days, the amplitude changes. But if it's much brighter, it's 10,000 times brighter, it takes about 30 days to make that cycle. Okay. And she realized that if I could measure this time of the brightness of the star, I could actually measure its intrinsic luminosity. This was a great discovery. And she coined the name that these Cepheid variables are like standard candles. No longer do I have to figure out now whether the star is close by to me or further away from me, and whether it's really bright or whether it's further away from me. I can just look at the brightness and tell you what is the luminosity. I think some of us, let me just try and make this build intuition to you. Think of yourselves driving in Goa roads at night. There are no street lights. And you are seeing this distant car coming towards you. And in the first, you see one light. The headlights are two, but you see one light. And as it comes closer to you, you kind of see that it separates into two lights, and these two lights are approaching you. You cannot have built in your head an intuition of how as it becomes two lights and as it's approaching to you, what is the approximate distance of this particular car which is approaching you? The same intuition is here now. By looking at the luminosity change in this star as it goes bright and goes down, and measuring its time, you could actually judge how far that star is away from you. And now you have a way to measure the distance to the star. So as soon as they discovered this technique in 1907, the people at the Hubble Observatory in 1920 immediately put it to use. So when they looked at the night sky, they could see the Milky Way, which some of you may know. It's this big band of stars in the night sky. In the olden days, you could actually see this in Goa. Now with all the street lights, it becomes less so. But this big band of sky in the night sky. And they also saw that there were some objects which looked like, which is called as globular clusters, which is around 10 raised to 5, which is about 10,000 stars, which they also knew, which are part of those messier objects I talked about earlier. So they actually realized they were stars. So what they did is they looked for Cepheids in all of this. They looked for Cepheid variables, all these Cepheid variables in these stars, in this Milky Way, and they looked for globular clusters, and they looked for Cepheid variables in these globular clusters. And by 1920, they put these two pictures together, the globular clusters and the Milky Way, and they made this image, this model of what our galaxy looks like. So they realized that there was something big and dense in the middle, which they called as the bulge. There was a long disk. You can see this red disk. There were some globular clusters in yellow distributed all around. And that they realized that the sun, which is this cross over here, can you see this cross, is about 8 kiloparsecs, 8,000 parsecs away from the center of the galaxy. And that the galaxy itself, this distance was about 15 kiloparsecs. And they estimated that the galaxy had about 1 billion stars. So by 1920, with that discovery of that lady, which we saw earlier, Henrietta Swan Leavitt, and putting these observations together, they immediately put together that the galaxy, that the universe now is this big. So now just imagine the big step we had from our solar system to the stars, which around it, which you could imagine is just around over here, just around the cross, to suddenly the universe becomes really big. It becomes really large. So from here, this cross, our universe becomes really large. And this was our universe, our concept of the universe in 1920. But there was a problem. And the problem is best illustrated by this great debate, which happened exactly around 1920 by two of the greatest astronomers of the era. One was Shapley, which you see over here, and the other is Herbert Curtis, which is this man. Both of them were working in the US. This was what he was working at the University of Harvard University, and Curtis was working on the West Coast. And the problem they had was about these messier objects, these nebulae. They looked at these nebulae and they couldn't understand where these nebulae were. So Shapley, who constructed this understanding of the galaxy, argued that these nebulae were actually, kind of floating around the galaxy like this. So this was his galaxy. This was the disk of the galaxy. Here the sun was over here, the sun and this yellow dot over here. And he believed that the nebulae were actually floating around here. They were within our galaxy. Well, Curtis argued, no, that these galaxies were actually much further out. These nebulae, they wouldn't call these Andromeda nebulae or all the other nebulae, were much further out. You can see these kind of elongated objects where Shapley put the nebulae, but Curtis placed them right outside the plot. So right outside the plot. This was this big debate. In the debate, of course, Shapley won, but as we know from how science progresses, the way science goes is our information of 20 years ago quickly becomes obsolete. And everything we know changes very fast. And so there was what changed things. Well, there was this man, his name is Edwin Hubble, and he looked at the Andromeda Nebula, which is over here, which I've showed you a picture over here. And he looked at an image of the Andromeda Nebula, and he found, as he marks over here in 1923, he marks out two Cepheid variables within the Andromeda Nebula, within this nebula over here. And he measures their light curves. And he immediately realizes, no, the Andromeda Nebula is not within our universe, or not within our galaxy, as they call them, but is much, 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 much further away. And that was the big news in 1925, where Dr. Hubble describes the mass of a celestial body 700,000 light years away. So he doesn't put the Andromeda Nebula close by, but he puts it really, really far away. What does this mean in picture? It means this. This is the Milky Way. What Hubble showed us is that the Andromeda is over here. And there's about 205 million light years distance between her. So you can quickly imagine a universe which was so big now, with Shapley in 1920, within 5 years, expanded so much to Andromeda. And this distance, so I reminded you that this was 15 kiloparsecs, kind of the radius of this galaxy, of the Milky Way. And the distance to Andromeda is about 800 kiloparsecs, which is so kind of a sense of how our concept of the universe expanded. Let's take a step further. Within a few years, immediately after that, a number of other techniques developed to find out distances to various of these galaxies, these other universes out there. Now we would call them galaxies. And over time, people actually, develop these techniques and stitch them together. So one technique, because some techniques work for smaller distances, like, trigonometry, like parallaxes, work for smaller distances. But for larger distances, you need Cepheid variables. For still larger distances, you need something else. And these, there are whole sets of different techniques which will become a little difficult to explain to you now, but they stitch them together. So one depends on the other. And you can then measure distances which are very small, 10 AU, which is within our solar system, to distances that thousands and thousands of times the distance from us to Andromeda. So you cannot build up what is called as this kind of a distance ladder. And it's really hard, but this is one of the most hardest problems to do in astronomy, is to measure these distances away from us. So what has happened now in this 1 century now to understand about these distances? Let me just immediately give you the results, what we know today. Now this image over here is taken with a telescope, which is a very recent telescope. It's called the Hubble telescope in space. And what it does is that it's looking at a patch in the night sky, and it's observing it for a long time. And the more you observe, the more light you see from further and further distances. So you can say that this image which you are seeing now is the furthest we can see in space. Now, we don't know what distances each of these galaxies are at. You can see thousands and thousands of galaxies. Probably the ones which are more brighter are closer to us. The ones which are really, really faint are very, very far away from us. And using the distance ladder and those techniques, so that they will try to get the distances from these distances. And these are more or less the results. Let me just show you a typical example. So, so suppose if you are positioned yourself over here, you are positioning yourself over here. This is the center of us, that means our galaxy. And as you look around, you see in this particular study, which was completed in the 1990, it's called the 2DF Galaxy Survey. You can see that they have here about 100,000 galaxies, approximately. And they measure the distances to all these galaxies in two kind of segments. And just to give you, I said, over here, I'm showing you the distances in light years. Billions of light years. This is 1 billion of light years. And to give you a sense of context, 1 billion light years over here is about 307 megaparsecs. That's about a million parsecs, right? 10 raised to 6 parsecs. So let's put it this way. Andromeda, which will be very, very close over here, just next to us over there, just very close over here. And what they immediately realize is that there are thousands and thousands and millions of galaxies spread out, and they tend to clump around each other. Today, so if you will look at this, so this goes to about, if this is 300 megaparsecs, this is 600, 900 megaparsecs, 1200 megaparsecs, 1500 megaparsecs. Today, in terms of this, we go out at least 5 times this distance. 5 times this distance. That's the latest surveys to do. So the universe has become much larger. It's like every 10 years, the universe, our understanding of the universe becomes even much more larger and larger. To a certain extent, that at a certain point, we are limited by the amount of light we see. Let me also explain to you a simple concept. If a galaxy is far away from us, and you remember from the slides before, the light from Alpha Centauri takes us 4 years to reach us. A galaxy at this point the light takes us 1 billion light years to reach us. This takes us 2 billion light years to reach us, and further and further. However, as we go further and further, we're actually looking back in time. So it's a very distorted concept of, as we are looking further and further in the universe, we see how big it is, but we're actually seeing as how it was billions of light years away, billions of light years ago. So the first thing I want you to realize is that our concept of the universe expanded in this century. And the reason why it expanded is that because we were able finally to measure distances. This is a thing to keep in mind. We were able to measure distances through various techniques we have developed over the last 100 years. We were able to measure distances to these very objects. And we have realized that we are a very small part of this very big universe. Let me move to the third point, which is the second point, but the third point of today is the beginning of the universe. One thing, when we look at a light, from a galaxy, the light changes depending on its motion. Now, many of you have experienced this, especially with trains. You know, as you hear the train is approaching us and the train passes us, the horn, the siren of the train changes in frequency. It's approaching us with certain sound, as it crosses us, and as it's leaving us, another sound. And this is because of an effect which is called as the Doppler Effect, which basically means the frequency of sound or light changes. One thing to remember is that if light is moving away from us, it becomes more red. It becomes red shifted, we call it. If light is moving towards us, it's called as blue shift. And so by looking at the Andromeda galaxy, for example, we can see that the Andromeda galaxy is rotating because one side is becoming red and one side is appearing more blue to us. So we actually see that the full thing is rotating. So if things are moving away from us, they become much more redder than they naturally are. Okay. So Hubble, this famous Hubble, who actually discovered that Andromeda was very further away from us, also made another substantial great discovery. He had measured now the distances in 1930. He measured these distances, 1929, let's put it. He measured these distances to various galaxies. Okay? He measured distances to various galaxies using these Cepheid variables. But he also measured their velocities through a technique which is, let's not worry about how they measure, but they measure the velocities. And when he plotted the velocity and the distance on a plot, he realized that there was a relation. That means the distance is related to the velocity. Galaxies which are close by to us are moving at a certain velocity. The further they are moving at a much faster velocity. So he coined this very famous relationship. The velocity is proportional to the distance. There's a constant over here. So it's called the velocity-distance relationship. What it's telling us is that all these galaxies are moving away from us. They are being redshifted. They are moving away from us. But they are moving in a very particular way. The further they are, they're moving faster away from us. Also mentioned that Father George Lemaitre, also proposed the same idea in 1927, based on a very theoretical concept, but it was actually Edwin Hubble who actually conceptualized this idea. So what does this mean? Let me try and show you with this diagrammatically in a small illustration. Think of us here in the middle, the Milky Way. We are sitting in this galaxy. And as we look at all these other galaxies over here, we see they're all moving away. They're all moving away from like nobody likes us, put it that way. But the further they are, they're moving at much faster distances. So if you think of the arrows here as the velocity, the further they are away, the further they are moving away. It's actually like everything is moving away from us. Now, I don't want to give you the impression that you may think everything is moving away from us, but this is if you think that we are the center of the universe. But if you look at it another way, now I'll try and illustrate this to you to another example. Think of balloons. All of you know what a balloon is. And think of all these galaxies on the surface of the balloons. And over time, you start blowing the balloon, and the balloon becomes bigger and bigger. Any 2 points on the balloon become further away from each other. But there is no center of the universe. Every galaxy, as it looks at its neighboring galaxies, also sees them moving away from each other. That means if Andromeda looks at us, it also sees us, or other galaxies look at us, they also think that we are moving away from them. So as time progresses, galaxies seem to be moving away from each other. It's like the universe is expanding. Okay? So this was a great discovery in 1930. And people didn't understand what this discovery meant. Now, I'd like to come to this protagonist, Father George Lemaitre. He's a Belgian Catholic priest. He was studying the equations of Einstein, the Einstein general relativity, and he was trying to understand what Einstein would say about the universe. And he looked at these observations from Hubble. And he conceptualized that if things, look over here, so let's think of, look at this figure over here on the right-hand side. So, and time is moving in this direction. So it means we are now here. This is earlier in time. This is still earlier in time. Earlier in time, things are much closer towards each other. As time progresses, things move away from it. So he conceptualized that if you actually go backwards in time, things become very close to each other. And finally, you can push it even further and it'll come to a single point. And he called this point, single point, as the primordial atom. What it means is that the universe started in a single point, a singularity. Or today, what we would call as the Big Bang. In fact, over time, this word came to be appropriate. But this theory was actually proposed by Father George Lemaitre in 1927. I like to say the Big Bang is a very Catholic idea. It was proposed by a Catholic Belgian priest. So let's see what this means, okay? So let's see what this implication means. Now let's look at so if you were able to extrapolate back in time, and you could measure the time from here to when it became a single point, that would be the approximate age of the universe. This would be the approximate age. And you can do that. So let's look at this diagram over here. This is what we are now, okay? This is time. It's not in linear units. It's called log units. So you can see that the units are slightly different. So 380,000 million, 300 million years, 1 billion years today. So if you look back in time and try and extrapolate it to a single point, you will come to a time, and that time is 13.7 billion years when the universe was a single point. That's the age of the universe. 13.7 billion years ago. When did our solar system form? To give you a sense of time, our solar system started 9 billion years after the Big Bang. So about, you can say, 4 or 5 billion years ago. The first galaxies appeared about 11 billion years ago, 12 billion years ago. The first stars appeared about around that time. And then everything else becomes dark because there were no stars before that. Okay? So now we have a revolution in our understanding of the universe. We know that the universe started from a single point. We know the approximate age of the universe. That age is about 13.7 billion years ago. So we know it through this way. We also know it through other ways. I'll just briefly mention that if you look at the age of the stars, and we have developed ways of developing the age of the stars, we can actually understand that this amount, 13.7 billion years ago, is approximately the correct answer of the age of the universe. But there is something else. As the universe, now think of your experiment. If you take a balloon, right, and you fill it with gas and you compress it into a single point, the gas becomes hotter. All of you have this experience from tires and things like that. So as you go back in time, the universe gets hotter and hotter. Okay? And there is a lot of not light in the sense of blue light, but there is also what is called as the background radiation, with all this red thing which you see here, which comes from the first a few thousand years of the Big Bang. And if this is true, this must have been very hot then. And as the universe expanded, this must have cooled down, and we should be able to detect this radiation from this just quickly after the Big Bang, when the universe was really hot. But now this radiation, which was very hot then, should become very cool because the universe has expanded. We have discovered this radiation. This radiation is called the cosmic microwave background. It is detected in radio waves. So think of the same kind of radio waves you listen to your radio, your microwaves. We detect it in that same frequency, in gigahertz. It's an echo of the Big Bang. Today, this radiation is very cold. It's at 2.72 Kelvin, which is about, think of it as minus 270, more or less, degrees centigrade, minus 200. It was first discovered by Penzias and Wilson in 1965. So immediately a confirmation very quickly of the ideas of Father George Lemaitre in the 1930s. And soon later, they also won the Nobel Prize for this discovery. This radiation originated 380,000 years after the Big Bang. Was very hot, but it cooled down over time. And it cooled down by a factor of about 1,000 times. It cooled down. And it cooled down because the universe was expanding. So this is the second big discovery of this century. We discovered the universe is very, very large. We discovered the universe is expanding. And we discovered that the universe is expanding, and if you extrapolate it backwards in time, it begins at a single point, which is called as the Big Bang. It was a very hot initial start. And we even detected the radiation from that initial big start of the Big Bang. So I would like to conclude then by trying and summarizing this. So before the turn of the century, 1900, our understanding of the universe was very small. We knew about the solar system. We knew about the distance to about 60 odd stars. Then, at the start of the 19th century, with the help first of the Cepheid variables, these variable stars, and various other distances, what we would call as standard candles, we were able to build up distance. And we quickly realized that the universe was much bigger. And the galaxies were much further away. It was a great expansion in understanding of it. And in a certain anthropomorphic sense, we can say that we are no longer the center of the universe. By no means. The third point is to remember is that galaxies are now receding away. They are moving away from us. The universe is expanding. Extrapolate back in time, you get to what is the Big Bang and the age of the universe, which would be about 13.7 billion years ago. I will leave the presentation and I will ask Mr. Savidais to share with you the PDF in case you have questions, doubts about what we saw and did not catch something well. Tomorrow we will take up the next 3 ideas of the century. That is the origin of the elements, so the origin of what are we made up of, the finality of the universe, what will happen at the very end, and the search for other planets beyond our solar system. And with this, I will end, and I will try and see if there are any questions in the into the chat. Okay, I will quickly look it up. My gosh, there is actually a lot of questions. So let's see if I can quickly.
A few of those questions have been answered by a few other participants, Father.
Okay. So quickly, yes. Let me put it this way. Let us stop at this point because it's already 10 o'clock at your place. I will quickly look over the chat today evening. I will try and collate it. I will see the questions which are not answered, and I will briefly at the start of tomorrow's session, I will answer some of those questions, and I will then start with the remaining 3 points. Thank you for your patience. Sorry for the technical problems, and I wish all of you a very good evening.
Thank you so much, Father.